So in this next recording, we're going to continue in our chemistry review. This information is also addressed in your book, but don't be afraid to crack open an old chemistry text to review pH. And with pH, we have to talk about acids and bases. But let's start with pH. What is that? Well, pH is a system to measure, ultimately, the hydrogen ion concentration in solution. So these are the two ions of interest that deal with pH, and they're the foundations of acids and bases. Now, throughout this talk and throughout the quarter, I'm going to use the word proton, hydrogen ion, hydronium ion, all kind of synonymously. Know that in water, that lone proton, which if you look at a hydrogen, you rip away the electron, all you have left is a proton. That is a hydrogen ion, right? It's technically going to be bound to water, and what's called a hydronium ion, which is H3O+. But again, the details of that aren't necessary to understand for understanding acids and bases. But pH then is a scale, right? It's a scale to measure the acidity or the basicity or alkalinity of a solution, and it ranges from 0 to 14, with the lower numbers being more acidic and the higher numbers being more basic. Pure water is by definition pH 7. We'll talk about why that is in just a second, but that is where the proton concentration is equal to the hydroxide ion concentration. Hydroxide ions being OH negative, right? So you can see that right in the middle of that scale. Human blood is slightly alkaline. So it's an algorithmic expression of proton concentration. So for example, a 10 to the negative 5th molar hydrogen ion concentration is pH 5. So literally, pH is the negative log of what? Hydrogen ion concentration or proton concentration. Now, 7 is neutral pH, and this is because of this characteristic of water, which is autoionization. So if you have water, a batch of water, it will spontaneously break down in very small amounts to this hydronium ion and the hydroxide ion. And so if you see H2O plus H2O and you have a double-headed arrow and your two ions on the right, you would say that this equation lays far to the left. So the vast majority of the stuff that's there is just water, but you're going to have very small amounts. Well, those small amounts actually can be measured, and what we find is they're about 10 to the negative 7th molar. And this is actually an equilibrium, right? So when you look at that reaction, you can get this ionic product of water, this Kw, this equilibrium constant of water, is going to be 10 to the negative 14th. But 10 to the negative 7th proton concentration or hydrogen ion concentration is pH 7. So that's where the 7 comes from, and then we're either going to increase the hydrogen ion concentration or decrease it, moving that pH up or down, right? So with that, then, we can say that these two concentrations are linked, right? Because it's at equilibrium. If we increase the hydrogen ion concentration, we're going to decrease the hydroxide ion concentration, making something more acidic. If we increase the hydroxide ion concentration, we're going to decrease the hydrogen ion concentration, making something more basic. And we're going to see how we do that with acids and bases. So when we add protons or hydroxide ions to solution, we're making it more acidic or more basic, and substances that dissociate completely and add protons or hydroxide ions are strong acids or bases. For example, hydrochloric acid, HCl, each molecule of that contributes one proton and one chloride ion to solution. So it's a 1-to-1 dissociation. Sodium hydroxide is the same way. For every sodium hydroxide molecule you add, you get a hydroxide ion, making the solution more basic. These are strong acids and bases. Now, because we're defining strong, we're defining it because you can compare it then to weak acids and bases. And weak acids and bases incompletely ionize when you add them to water. And this is very important because weak acids and bases are going to be much more useful to a biological system when we get into buffers. But we'll get there in another recording. Now, if you've taken the intro chemistry class, you know you've done the lab, which is the titration of the strong acid. And so you start off with a solution that is in low pH, it has a strong acid in there, and then you add very small amounts of strong base. You're literally canceling out every free proton in solution with a hydroxide ion until you reach that point, that equivalence point when they're equal, and that's going to be at pH 7. It's really tricky to do because it's based on a color change when you're doing it in the lab, and it's very easy to add just a little too much hydroxide, and then boom, you're over into the pink. So those of you who are familiar with that understand exactly what I'm talking about. If you haven't, take the intro chemistry series and then you will know. But the point here is that this curve is very, very steep in the middle. Like you go from almost always being acidic to almost always being basic very quickly, and that doesn't bode well for biological systems, right? We need to be around that pH 7. And so this is kind of a precursor to the buffers, which is going to be our next recording. But I want to lay this foundation down now and talk about some different definitions of acids and bases. So if we use the Bronsted-Lowry definition, we talk about anything that's an acid as a proton donor. They're going to donate that proton to solution, and anything that's a base is a proton acceptor. So we're going to focus exclusively on the protons, which, when you think about pH, is a fine thing to do. Now, what really gets powerful is when we start talking about conjugate acid-base pairs, right? So now you talk about ammonia, NH3. When you add ammonia to water, you get an ammonium ion, NH4+, and a hydroxide ion, as you've kind of taken one of those free protons out of solution. So ammonia is literally a conjugate base. So it's actually a proton acceptor. And then the ammonium ion is technically an acid. It's a conjugate acid. It's going to be a donor. Now, whether or not it's a donor or acceptor depends on the environment. Where is the pH of that water to begin with when you add the ammonia? This is what we're going to talk about more as we talk about buffers. But you can actually calculate that tendency to lose or accept a proton, and we call that the pKa. All right. So this is a really important term, and we're going to address it again, and we're going to see it again throughout the quarter. But the pKa then is the tendency that is characteristic of a substance to donate that proton. The bigger that tendency, the stronger the acid. But it is also an equilibrium, and that's going to be very important to use weak acids and bases to control the pH of a solution. Now, to go into a little bit of a biology here, if we protonate or deprotonate histidine, we see that it can have a big effect on proteins. Histidine is an amino acid. That is the monomer that makes up the polymers that are proteins, and we'll talk about that later. But you can see its pKa is 6.5. And another way to state pKa, which I'll talk about in another recording too, but the more you hear it, the better, is that this is the pH at which half of the histidines in solution will be protonated and half are not protonated. So this is an area where half of the histidines, which are on proteins, could be donors and half can be acceptors, and that's going to act as a buffer, really. But you can also see that when I am in a donor form as a conjugate acid, I'm positively charged. And charge, as we've already seen with the characteristics of water, can impact how molecules behave. And so if I have a protein that has charged histidines, it's going to react differently and be shaped differently than a protein with uncharged histidines. And we're going to see that this is why we need to understand acids and bases and pH, and this is how they have a big impact on biological systems.